Welcome back to the classroom. My name is Mr. Wong, and today we're going to be going through another past paper question in physics. This is for circular motion, so Module 5 of Inquiry 2. This is the 2013 Victorian paper, question 4. We have a group of engineers trying to design a curved road for high-speed railway. To prevent excessive wear and for the comfort of the passengers, it is important that the track be correctly banked so that there is no sideways forces between the rail and the wheel of the train. So this is what we have in 4A and 4B. The radius of the curve is 2,000 meters and the speed of the train is 50 meters per second. It says on figure 4B, draw two arrows to show the external forces acting on the train and a third arrow to mark the net force on the train. So this is what we have. The first one obviously being gravity. We know that is always going to point downwards. The second force that will be acting on our train here is the normal force, which always acts perpendicular to the surface of contact. So that's what we have here. The net force is obviously our centrifugal force, and therefore it is going to go towards the center like so. And that's how you do the first problem there. Now, next question we're going to go to, it says calculate the correct angle of bank for the track to, let's read that again. Calculate the correct angle of bank for the track so that there is no horizontal force on the wheels on the track. Show the steps of your working. You probably need that rewording. So the question is how much angle needs to be lifted in order that when this object is going in circular motion, it's not rotating or pushing towards the right or pushing down towards the left. This comes back to where is the origin for the centripetal force if it's a banked road? Well, it all comes down to our normal force. If I draw this out again, just so it's a bit more clear, this is our normal force, this is our gravitational force. Our normal force is at an angle to this particular surface, which means it will have a horizontal and a vertical component. The vertical component is this bit here, which is basically equal but opposite to gravitational force. And we have this normal force x component, normal force y component. The y component will cancel out Fg, and so Fg doesn't actually contribute to our centrifugal force. However, the horizontal component has nothing to interact with, and therefore this is the reason why there is centripetal force or net force as the object is going in circular motion around a banked road. So let's write that down. So our centripetal force, which is given by the formula of mv squared over r, equals our normal force x component, which is also, we could write in this context here, it would be the sine component of our normal force. Okay, but we don't have to get into that complexity, and let me show you not sine. We don't have to go into that complexity, and let me show you why. In this problem here, mass has not been given to us, so we don't actually know what mass is, but we know what radius is. It's 2,000 meters. We know what the velocity is. It's 50 meters. Now, since we're dealing with the same mass, let's say instead of using centripetal force, we use centripetal acceleration to find us the answer. So v squared over r, so I'll just write no mass, hence use acceleration. So v is 50, r is 2000. So my value for acceleration is 1.25 meters per second squared. I know the acceleration due to gravity is negative 9.8 meters per second squared. So if I draw this back out again, draw my triangle. So I have my triangle like that. Theta is this angle here. This value is AC, that is 1.25. This is the value of G, which is 9.8. I can use tan theta to solve for my answer. So the answer would be theta equals to tan inverse. In this case, because we're just trying to find the value, we don't need to worry about the signage here, but it would be 1.25 over 9.8, and we're going to round it off to two significant figures, because that's what's given to us in this problem here. So I'll just put that into my calculator, and we get about 7.3 degrees. Okay? And that's how you solve this problem here. So if you weren't given the value for the mass, you could work your way around it by using acceleration. If you found this video useful in explaining vector diagrams and solving for problems in circular motion, like, subscribe, and I will see you next time.